So with all that, welcome, and I'm excited to introduce today our talk given by Dr. Aaron Danielson and Lucas Wu, and the topic today is whether crossing the ball in soccer is a good strategy. So Dr. Danielson is a postdoctoral fellow in the Department of Statistics and Natural Science here at SFU under the direction of Dr. Derek Bingham. He has his Ph.D. in statistics from UCLA, and he also has master's degrees in economics and in policy analysis prior to his Ph.D. As he was completing his doctorate, he spent 3 seasons working as the Associate Director of Analytics for the Los Angeles Lakers, where he provided coaching staff and management with statistical insights on a variety of topics. His academic research focuses on statistical methodology for applications in the natural sciences and sports. And when time allows, he volunteers as an analytics advisor for the SFU men's basketball team. Lucas is a PhD student in statistics supervised by Dr. Tim Swartz and Dr. Dave Campbell at SFU. Dr. Campbell is now at Carleton University. He is interested in sports analytics, causal inference, and statistical machine learning. In 2019, along with Danny Chu, Matthew Rayers, and James Thompson, his team was the winner of the NFL's inaugural Big Data Bowl in the college division. So I'm very pleased to turn it over now to Dr. Danielson to kick off their talk. And as Aaron's getting set up, is there any questions for me or regarding the seminar series and the format? If you want to just maybe use the group chat and then I can try to answer your questions.
All right. If there are no questions, then I'll go ahead and get started. First of all, I just want to thank everyone for showing up virtually today. And I think it's also important to just express how, how grateful I am, and hopefully, we all are, to be healthy at a time like this and to be able to talk about sports when such challenging things are going on in the world. So, yeah. Thank all of you, and I'll get started with the talk. Okay. So the primary question we're interested in today is whether or not crossing the ball in soccer is a good strategy. And so, well, what does that really mean, right? And so the question we're asking is crossing the ball increase the probability of getting a shot attempt during an attack? And I'm playing a clip right now, the LA Galaxy game, and you see one player over on the side of the field kicking the ball towards the middle of the field to a teammate who then attempts a shot. And this is a canonical example of a cross. So this is the phenomena we'll be studying in detail today. Okay. All right. So kind of an outline of the talk before we get into it. So some recent research papers have called into question the benefit of crossing the ball. They found some different results, but seem to suggest that not all teams should attempt it. They shouldn't make, perhaps teams that are good at it shouldn't do it that often. But this is kind of contrary to the knowledge of soccer experts who frequently believe that crossing is a very valuable strategy. And so it's important to note that the prior statistical work is associational in nature and not causal. And so what that means is, many factors are at play here, including the spatial configuration of the players, the offenders, defenders, goalie, and the ball at the time of a cross. And so our core question today is, what's the causal effect of crossing on the probability of a shot attempt during an offensive attack? So to quickly summarize things, we do find that crossing the ball increases the probability of a shot attempt. So there do exist contexts where this is a good strategy. And we'll hear a lot more from Lucas on those contexts later on in the talk. So here's the outline. So I'll give a very short review of the basics of causal inference. So this is a huge field of literature. We'll just touch a very small part of it, and we won't go very deep into that ocean. So for those of you who know a lot about it, you'll be fine. For those of you who don't, we'll try to present enough information so that you can follow along in a meaningful way. Next, Lucas will discuss a matching analysis of crossing. And so that'll be an applied section where you'll see some subject matter answers. Next, we'll introduce some limitations of our approach. So in our approach, what we're doing is we're taking the spatial configuration, so i.e. again the offensive and defensive positions, the position of the goalie and the ball, and we're transforming it to a set of interpretable features. And then finally, we're going to suggest a novel method for causal inference. We call it spatial surface matching as a general method for causal inference in Swartz Analytics when spatial temporal data is available. All right, so part one, basic problem of causal inference. So over on the right of the slide here, you see a directed acyclic graph. So the nodes here are random variables. And you see links connecting the random variables, and those are meant to indicate what we believe are causal relationships. So in DAGs, unlike, for example, in dependency graphs, you see links with no arrows, right? Because the person positing the statistical relationship is not saying anything about causation. Here we are. And so let me review some of these random variables because they'll be relevant throughout the rest of the talk. So first of all, T here, the yellow node, that's the treatment, and that will be crossing the ball. So it's a cross attempt. Y, the green random variable, is the outcome, and that's a shot attempt. Okay, so keep in mind both T and Y are binary random variables. The red node you see, so that's going to be the spatial configuration, right? And then I also have an X and W. Those do not play a large role in the analysis, but they're there just to show that you can have other random variables that influence Y and that and influence T. Okay. So the idea here and the assumptions that we're bringing, and this is important whenever you construct a DAG like this, you are making assumptions. Assumptions we're making is that the crossing causes the outcome, right? And we're also making the assumption that the spatial configuration causes both a cross attempt and the outcome. So what we see here, and this is the core or one of the core problems in causal inference, is that the relationship between T and Y is confounded by Z. So that is to say, because Z is causing T, there's an indirect effect of Z on T onto Y, right? While Z is also causing Y. All right, so what this means is that some units are more likely to be treated according to the shared influence from the spatial configuration. So what that means is, certain spatial arrangements are more likely to result in a cross attempt. And it might also be true that certain spatial arrangements are also more likely to produce a shot attempt, right? And so this makes it difficult to identify a causal influence. All right, so what do we do? Well, we need to break what's called a backdoor path between our treatment variable and our outcome variable. So if you can see my cursor here, I'll just trace this backdoor path. So here we are at the treatment, going over here to our confounder, and then down to the outcome variable. All right, so there's a broad theory developed by Judea Pearl and many others, but because I'm a UCLA guy, I'll talk about Pearl. And so in his book on causality, he describes and proves many results, giving us conditions under which all backdoor paths are blocked. And when all backdoor paths are blocked, we can identify the causal effect of the treatment on the outcome. Okay, so in our case, we have only one to block in this very simple graph. And so this is accomplished by setting our conditioning set here. So this is my calligraphic Z just equal to the spatial configuration, right? All right. So again, I'm not going to go too deep into the details here. There's a huge literature for those curious on learning more and how all this works. But we'll take this as a point of departure. Okay. So the idea of causal inference is to approximate experimental conditions. So in a controlled experiment, we have no confounding, right? We assign the treatment randomly to units. And so this is an idealized situation, right? And when we have these conditions, when there no confounding or randomized assignment of treatment, we can talk about a random variable we call the potential outcome. And that's this y with the superscript t equal to tau. And so that's saying this is the random variable when you do tau, right? And so the intervention, so not allowed to naturally occur, but is set as if you were in a laboratory, right? So it's a different type of random variable than we typically encounter in statistical work. In observational studies, of course, as we just mentioned, there can be other variables that have a shared influence on the treatment and the outcome variable. And so we're looking at associations rather than causal relationships. And so a primary goal in order to do causal analysis is to define an interventional probability distribution rather than an associational one. So again, Pearl shows the following relationship. That we can define the probability distribution over the potential outcome, and that's what's written over here on the left. And then in the center here, so this is Pearl's notation for the intervention, so the so-called do operator. And what this turns out to equal in this current context is the following: we're conditioning over z, so we're taking the expectation over all possible values of the z. So that's all. So it's integrating, for example, over all possible spatial spatial configurations. All right. Finally, we can define a theoretical average treatment effect for a binary treatment as follows. So we have the expected value of y given the treatments present, less the expected value of y given absence of the treatment, and again averaging over all possible spatial configurations. Okay, so we can write this equivalently in terms of the potential outcome notation, and that's what we've done right here. So same thing, just looks a little bit different. So we have this theoretical quantity, and we want to estimate it. This is an empirical estimator. Again, you can read quite a bit about how we get from here to here, and so I included this reference here for Imbens and Rubin's 2015 book on causal inference. Give you plenty of information. An estimate for the average treatment effect, so E equals an average difference between potential outcomes. And so here our Y's are wearing hats because we're going to use data and we're going to estimate something. Now, so what we would like to do is we would like to compare the outcome variable if it had the treatment and if it didn't, right? But reality doesn't work like that, right? Things are realized one way. so there either was a cross in a possession or there wasn't, right? And so that means for each of these, we're only seeing so for each of these, we only get to see one, right? And for the other, well, we have to impute that value, right? So there are many different ways of doing this imputation, but the one that we'll discuss today are matching methods. And so matching methods have a long history, but they have a particular appeal because they're fairly easy to understand, and they allow us to have and we can also avoid defining a probability distribution over the outcome model. All right, so as I've said, one way to block the backdoor path between the treatment and the outcome variables to match untreated observations to treated observations. In a perfect world, the matched observations would have the same value Z, right? I.e. the exact same spatial configuration. Because if this were true, then they'd have the same probability of receiving the treatment, thereby removing the confounding, right? Of course, this is not feasible in general, and so will be in practice, most matching is approximate, and so there's always a little bit of bias that's introduced. All right, so a conventional approach is for all the observed treated units, we can choose the closest untreated unit, right? And so choosing the closest means we have to have some idea of distance or some kind of metric. And again, there are many ways to do this, but a very simple and straightforward way to do that is so-called propensity score matching. So there are a few steps here to do this, and Lucas will walk us through these in just a minute. But first, we create a probability model for the treatment, and this is called the propensity score. So again, the treatment is a binary random variable, so we're pretty well acquainted with these types of models. Next, we're going to compute the fitted probabilities for the treated and untreated units. And then lastly, we'll match observations according to the propensity score. All right. So I've created a little picture here that'll give us an idea of how this works. So over here on the left, these are my treated units, right? And over here on the right, these are will be my control units. And so you see these range from 0 to 1, because we can interpret them as probabilities, probability of receiving the treatment. And then same thing over here. So for example, let me take this light blue observation here. We see this is matched with this control unit. So that's the one that is closest in absolute value. All right. The other thing we see is that there are many different matching procedures. And then for some, it's possible that two different treated observations can be matched to the same control. And that's what we see is happening here, right there. Okay. So as we proceed through this talk, you can kind of keep this image in your mind. But this is what's going on. So we're taking what's really a kind of a high dimensional problem, right, and compressing it down to a single dimension, and that's i.e. the propensity score. Okay, so that's a very brief introduction to causal inference and a solution via matching in a few minutes. Again, we didn't want to get too far into the details, but give you enough information in order to follow the rest of the talk. So the next section of the talk will be given by Lucas, and so he's going to present a detailed analysis of causal analysis of crossing in soccer. All right. So I'll stop sharing and I'll hand it over to.
So Aaron, just before you stop, there's 3 questions.
Sure.
So I'll read them out. So if Patrick and Alon, you could just be online and to follow up. But so going back to your original, the directed acyclic graph, the question was, are W and X multiple additional features or one additional each?
They can be either, yeah. So this is abstract. So so the idea here is that X is a set of random variables that causes Y but doesn't cause T, right? And that W is a set of random variables that cause T and that they do not cause Y directly, right? So you might think of this other ways, right? We could also introduce a set of non-spatial variables that cause both T and Y. For simplicity, and for exposition, we'll just think of Z as the spatial features, right? Reality is always more complicated than a picture.
Yes. Okay, so Patrick, hopefully that answers your question. There's another couple of questions from the slide. So from Alon, it looks as if the assumption is that a cross definitely causes a shot and that there isn't any other outcome. Don't we need to include some sort of additional potential outcome, at least not a shot, as the alternative?
Oh well, yeah. So what this is saying is that the probability distribution for tau or for t causes the probability distribution for y, right? So it's a cause for both the outcome to happen or not to happen. Now, so there's a broad literature about comparing direct acyclic graphs. If you thought that it had no effect, then what one could do is you could take all of these random variables and multiply the whole system together, in some kind of likelihood model, right? And then compare the likelihood of the graph with the link in versus with the link out. And you get a ratio, right? And that ratio would tell you something about the validity of one graph over another. That's not what we're doing here. That's kind of like the discovery of directed acyclic graphs. Rather we're making this assumption, and so this assumption is founded on preliminary data analysis that indicates that this is likely the correct graph.
Right. So this is a theoretical abstraction,
Yep.
obviously simplified.
Yep.
So the second follow-up question, is it not important to question negative possible outcomes, that is like a fast break as a result of poor positioning due to a cross or similar?
Is it well? Oh, we're not saying it's not important. So I'm sorry, I don't know if I got what that's really asking.
Yeah, maybe I'll ask Alon. Can you just jump in and rephrase the question?
What I meant, like when you build this graph, you're looking at the possible effects on making a shot, because you determine that having a shot is sort of the quantifiable effect of a good tactic or not, which is understandable. But one of the things as a soccer fan that you worry about is what moves on offense expose you to greater risk later on defense.
Yes.
And so when you judge the successful strategy or something, you also need to consider that. I think maybe.
Yeah, absolutely. So this is a static DAG. There are dynamic DAGs, right? And so what in a different model that one could specify, for every possession, you have a DAG, and then the result of in possession t-1 is then a cause for whatever occurs in possession t. So we're considering a static case, but yeah, such structures exist, and that could well be important, and it's probably a good follow-up analysis. It's a very good question.
Great, thanks a lot, guys, for the questions, and Aaron for the answers. So just one last question from me, and it's, if we were to summarize this, so for some people on the call, maybe are more familiar with epidemiology, like this seems very analogous to a case control type of design, right? So we have observational data, we have the cases, which are the crosses, and then the control data, which are basically the spatial configurations that are similar to when the crosses happened, but then a cross did not happen, or maybe it's the shot. Can you just clarify that for me?
Yeah, sure. Oh, yeah. So let's put it into a medical context, right? So for example, let's say Z is, so treatment is whether or not someone takes some kind of vitamin, right? And then let's say that Z is something like someone's general, their care of themselves, right? And let's say Y is a health outcome, right? So perhaps those who take better care of themselves, right, are more likely to take vitamins, and then therefore, because they're more likely to take vitamins, they'll have a better health outcome. But those who take better care of themselves, perhaps by exercising or whatever story we'd like to tell, they'll also have better health outcomes, right? So you can definitely map it back to an associational study and in health studies. In a randomized study, what we would have is, here we have some background features of patients, right? And then this link would be missing because whatever medicine or treatment that we're assigning to individuals would not depend on their background features, right? And so it's an important distinction. Yeah, thank you.
Excellent. Okay, let's move on to Lucas's part.
All right, I'll stop my share and pass the baton over to Lucas.
Great, thanks, Aaron. Okay, so Yeah, so this project is mainly about contextual analysis of crossing in soccer using causal inference. So I will first like to thank my collaborators, so including Dr. Aaron Danielson, Professor John Hu, and also my supervisor, Dr. Tim Swartz, for helping and guiding me throughout the project. I will also give you guys a little bit background on the data set we use. So we are very fortunate to have this paired tracking data from the Chinese Super League, where we have 30 games of Shandong Runnan Taishan Football Club back in 2017. Oh, and by the way, so the background behind me is actually the stadium of Shandong Runnan. So I just put it for reference. And the data set comes in at a rate of 10 times per second. So we have all the X and Y location for all the players and the ball on the field. And for a single game, so we end up having roughly 1 million observations. Here's what the data looks like. Yes, sorry, like this GIF doesn't seem to work when I try to present this. So yeah, so here's a base trying to show you guys what does the data looks like for the first 10 seconds. And then, and theoretically, so the dots will move, and then you can see how this game progress like over time. And that's basically what the player tracking data looks like. And our project focused on crossing in soccer. So according to Wikipedia, a cross is defined as a medium to long range pass from a wide area of the field towards the center of the field near the opponent's goal. And as we know, so an image is worth 1,000 words. So I'm showing you guys a video clip right here. Okay, so that's a beautiful goal. And previously there has been some research already done in crossing in soccer. So for example, both Venser and Sarkar have looked at crossing in their research, and both of them conclude that crossing has a negative effect on scoring in general. And this kind of motivates our research. So first of all, so we believe so the previous research is looking at the crossing on the aggregate level, but what we believe is that not all crosses are created equal. So looking at the aggregate level does not account for the context and the quality of each cross. And we also know from like a stats 100, like correlation does not mean causal relationship in this case. And if you are interested in causal inference, I highly recommend you to read more about the work by Mike Lopez and his collaborators, who has done some awesome job in causal inference in sports. And I put these two references over here. And for this project, so we are hoping to answer this question: will a cross lead to a shot more often or less often comparing not crossing? As Aaron and Dave mentioned earlier, so in our approach in analyzing crossing is very similar to what a medical study looks like. So in a classical medical study, if we try to study, maybe the effect of a medicine to see if we can reduce the patient's blood pressure. So we first kind of try to focus on the study population. And then the study population, and then we know each individual has a slightly difference. So here, so the blue might represent, maybe the gender, like maybe blue represent the male, and then the green represent female. So, they have these individual characteristics in this population. And then the doctors will kind of randomly assign people into the treatment and control group. And then another important point here is you're hoping to kind of balancing this individual characteristics between those two groups. And then you want to assign maybe, like equal number of male and female in both groups. and you don't want to assign like all the female into one group and all the non-female into another group. And in that case, your study might be problematic. So after you have done this treatment assignment, and then, and the doctor will follow up with the patients, and then just to measure, for example, their blood pressure to see if there's a decrease or increase. And then once you measure the average, the blood pressure of the treatment group, and then measure the average blood pressure of the control group after taking the medicine, and then you compare the difference of those two. And that quantity is actually what they refer as the average treatment effects. And then to look at if the treatment is actually improving or not improving the patient's condition. So, and here is how we kind of tailor this into the crossing context. So in this case, you can think of the treatment will be the cross, and then the control group will be the case when the player choose not to cross. And also important distinction here is, in the previous medical study, we can have this randomly we can do this randomly assigned procedures. But in this case, player choose to cross and choose not to cross. So this is not randomly assigned. So we have to borrow the methods from causal inference in order to approximate this random assignment process to make this study more robust. And then in the previous example, so the outcome is the blood pressure, and then the outcome in our case will be the shots or short attempts. And then we measure, on average, what's the average proportion of the short attempts from crossing, and then what's the average proportion of short attempt from non-crossing group. And then we compare the difference of those two, and that gives us the average treatment effect for crossing. And then the first thing is define the kind of the population structure. So here, so I'm showing you guys all the crosses in our data set, and then it's overlaid by the kernel density, showing where would be the hotspot on the field, and then I normalize the attack direction from left to right, so that every per session, every team is going to the right. And as you can see, it's kind of aligned with what we saw in the Wikipedia definition. So the most crosses coming from the wing of the soccer field, and then we end up to choose kind of these two regions as the potential crossing regions, because it's important to compare apples to apples. So because for all the crosses here, so it makes sense to compare a non-crosses event within these two regions. And it doesn't make sense if you compare like a non-cross region, which is maybe back in the opponent's goal, or like somewhere near the midfield, because those are not the same thing. And you might also have a question about we're leaving out some data outside those two regions, and then we actually look at those data set, and then those data set is kind of so the definition of cross is kind of blurred compared to a pass. So and those observations is kind of it's literally a pass instead of a cross. So that's why we think it's okay to leave those out as well. And we also kind of create this perception sequence in our data, because in soccer, so the game is dynamic. So and then if we try to match a cross event with a non-cross event, the event that's most likely to be being matched would be another event within the same per session, because they have this kind of high correlation within a per session. So we first we kind of group those per sessions, we group those per session, and then we think between each per session that should be independent, and then that kind of will be more realistic to our assumption. And then the figure on the left here is the per session sequence with the crossing attempt. As you can see, the play start with here, and then the player dribble the ball and then pass, and then enter this potential crossing region, and then eventually he made a cross right at this spot, and then his teammate receive the ball and then take a shot, and he actually result a goal in this case. And the figure on the right here is a per session sequence without a crossing attempt. So basically, the player enter this potential crossing region or potential crossing zones, but he chooses to do something else. In this case, he chooses to dribble, or he might also choose to to pass the ball. He can do anything other than cross, and that will be considered as a procession sequence without a cross attempt. And then the next thing here is we were trying to, creating this contextual variable, the contextual features that will explain, best what a cross is. So here, remember this like snapshot from the video we have seen earlier. So, and this is, I think this is at the moment of the cross. And then you can kind of imagine what might be important in this case. So, and then we kind of roughly divide it into kind of two groups. So the first group will be what's important for the sender. So, and then as you can imagine, like how fast the sender is traveling, the speed of the sender, and then the nearest defender of the sender, and also the space available to the sender according to Luke Braun's pitch control model, and also where the location of the sender, like how far away is he from the sideline, how far is he from the end line, stuff like that. And then we also create another feature which is relevant to the potential receiver. So which will be the number of defensive players in the box, and also the number of offensive players in the box, and also kind of calculate the ratio of those two numbers. And then also maybe the goalie position might be important here as well. So after we create a set of features, and then this is the features that are important when we fit into a logistic regression. So we can use other kind of machine learning, deep learning method to fit this model. This is basically a classification problem. But we think logistic regression is more interpretable in this case, and then I think it will be helpful for us to get interpretable features and an interpretable interpretation. And here, so one interesting example might be maybe Z1, which represents the Scott differential, and then the coefficient is negative and is highly significant. So which suggests that if the team is behind, and they are more likely to cross, and then this is kind of aligned with what we observe in the soccer game. And another interesting example might be the number of offense player to the defense player in the box. So this coefficient is 1.8, and then the standard error is also small. That means it's also another highly significant variable. So if the ratio of number of offense player and defense player is high, so that means you are more likely to cross. And as Aaron mentioned, that propensity score matching is essentially summarize all these like high dimensional feature into one number. So we are attaching like one number to each observation, and then this number is ranging from 0 to 1. So 1 means you're more likely to cross, and 0 means you're less likely to cross. So, and then if we assign this number for both the treatment and the control groups, and then we kind of measured the closest or the smallest distance in terms of propensity score, and then we have this kind of match pair that is gonna help us for the analysis later on. So in this case, so for a given treatment group, for a given cross, we match another non-cross with the most similar propensity score. In this case, will be maybe 0.2, and then here, so we have another cross event, and then which is maybe 0.8, and then we match another close related observation in the control group with a similar propensity score. And here's an example of showing with the event where we have the probability of cross equal to 0.82, and then the match here will be 0.84. And then I'm showing you guys this kind of the raw data, the spatial data. What does it look like? So, and at the first glance, it looks kind of drastically different. But and please bear in mind that in soccer we can kind of so they have different symmetric features. So if we kind of do a mirror image from top to bottom, so and then they should kind of reflect like similar situations. So if we flip this 24, to the other side, so that's kind of looks more closer to to the match case on the right hand side. And then and then the dot being like circle, that means the ball carrier. And then as you can see, like the ball carrier 24, they have kind of similar nearest defender distance compared to the control group, and they are running roughly the same speed. And then if you look at the potential receivers, so the ratio between the offense and defense players in the box, so they're roughly kind of equal. They have 2 offense players here, and then here we also have 2, and then 4 defense players, and then this is 5. And as we can see, so this matching process actually provides us some kind of intuitive interpretation. And later on, so Aaron will mention that instead of doing this kind of creating the feature and then match based on the feature, we can also create a surface based on the the location of the offense and defense players, and then we match based on the surface. That would be an alternative way to do the matching process, to do the matching. And then imagine we do this matching for all the observation, and then here's the distribution of the propensity score before and after matching. So before matching, so they looked, these 2 groups, they look really different. So the cross is the treatment group, and the non-cross is the control group. And then after we perform this matching, so we look at the distribution of these 2 groups, and they look really similar, which means we have done a good job of kind of balancing between the treatment and control group. Yeah, and then finally, so here's our result. So the average treatment effect we get is 0.05, and then the standard error is 0.02, which also suggests a highly significant effect. And then the interpretation will be, a cross will lead to on average a 5% more shots compared when you're not crossing. And then the figure below here, I'm showing you kind of the shot probability as a function of the propensity score. And then as you can see, if the propensity score is around 0.6 to 0.8, so they have a higher value compared to non-cross. So it means so crossing on average should have a positive effect in those range, and we offer kind of alternative insights that crossing might be beneficial in terms of creating more shots. So lastly, I would like to thank Danielson for providing us the data set, and also thank Danny Chu and Matthew Rice for their helpful discussion. And then I will pass this back to Aaron.
Are there any questions for Lucas before we move on?
So I haven't gotten any by chat. So just be mindful of time. We're at 11 o'clock, so we'll try to finish things up as promised.
Okay. All right. So I have some more material here. I'll move through it briskly, so we don't belabor the point too much. Okay. So yeah, Lucas, thank you for that. So this next part, I'll briefly discuss the need for spatial matching procedures. Okay, so here's a second look at our DAG, and so what this is kind of what's really going on, right? Remember, our original DAG just had Z, but what we've done is we've transformed Z, i.e. the spatial configuration, into a number of interpretable features. Now we can put these into 3 separate groups. The elements of Z that cause T, the elements of Z that cause Y and T, and the elements of Z that cause Y. When I mean elements, I just mean, think about when transformed, these transformed features cause the downstream variables. Okay, so so now in reality we have 4 backdoor paths, and we have now our conditioning set becomes slightly more complicated. That's all fine, right? So if we believe this is right, then everything's okay. But the question is, what if there's something in Z that's not contained in these 3 that causes T and causes Y, right? So you can imagine another node here, boop, and then arrows going to T and to Y. Well, omitting this, omitting a variable like this, or set of features such as this, that's going to introduce bias into our estimates. Okay, so the question is, are we using the spatial information to its fullest extent? We know that uncontrolled confounding will bias, or can bias, estimates of causal effects. So as an alternative to the approach you just saw, we propose to transform the spatial configuration into surfaces. So think of these surfaces as image files. So for example, a grayscale image file. You have an image, right? And it's a collection of pixels or grids. And within each grid, you have some value representing how the concentration of color, right, or how dark it is, right? So then one can match the treated and untreated surfaces according to their similarity, right, of these image files. So think about it this way: deep learning methods, they work by discovering abstract features, things that are not obvious to human beings, right? And so in the story we just showed you, we think, oh, here's an intuitive story about the things that likely influence. However, it's likely that we can't pick up all of those things, right? And so this method hopefully can produce better results in situations. All right, so very briefly, so this doesn't go over too long. So the first thing we have is transform the spatial configuration into an image. So I'll show you an example in just a second. 5 offensive players and 5 defensive players, a goalie and a ball. We'll take a grid. So for example, 30 by 20 field, and we'll put it into, say, 0.5 by 0.5 squares. So we'll call those pixels. And then each pixel is going to have an X and Y location. So then a surface, S, will contain 1 through mx times my pixels. All right, so now that we have these pixels, we need to give them a value, as in a grayscale value. And so one way to do that might be through kernel regression. So for example, the value of pixel I, Si, might be given as following, as a common kernel regression estimator. Okay. And so here the PJ are evaluation locations where we're either observing a binary random variable, or we observe a binary random variable that indicates someone's standing there or not. So let's see the picture, and that'll make things make a little bit more sense. So here's an example of a smooth surface. So here the O's are the offensive players, the X's, as you might guess, are the defensive players. The purple diamond is the ball, and then the triangle's the goalie. So here we've smoothed it over. And you see here, if you look closely, it's actually pixelated, right? So in all these little pixels, there's a numeric value, right? So it's akin to an image file. So then our idea is to compare surfaces. And there exist some distance functions, for example, the image Euclidean distance, that we can use to define the distance between images. And so in the interest of time, I won't go too much into the details here. But the idea is that we have the difference here between, so this is in pixel I, this is the difference in concentration between S and S prime in pixel I, and this is the same thing for pixel J. And then Gij is a weight applied, giving it, it's telling us how important the relationship between pixel I and J is. And as we see down here, using a Gaussian function, that can be determined by the distance between the pixels. So that'll define a distance between our images. So here's our idea now for matching in this context. So we could do the same as we've done before and do a nearest neighbor matching, or like an M nearest neighbor matching, for example. But another idea is, well, what if we can turn this into an optimization problem? And so for each treated observation, and here I'm going to index that by the letter R, we'll choose non-negative weights to minimize the distance between. Here's our treated, and then here is a convex combination of the untreated. And since it's a convex combination, we'll specify that it has to, the weights have to sum to 1. So this will result in an optimal weighting and produce better matches than we'd otherwise have. So then we can define a matching estimator. And so this is an example of, we saw this earlier in the talk, and then this is again giving us the idea that each one of these we either observe or we impute using the other population. So we've run some simulations on this, so here is the red line for some simulations that we've done. This shows the true average treatment effect, and this shows our optimal match in our using optimal matching and single matching using the spatial matching. So this is a preliminary result, and we're still working out some details. But I think that this can be particularly useful when when there are very complicated processes that determine the random variables in a system, and it's not easy to enumerate all of the interpretable features that one should put into a model. So the more complicated the sport, or the more complicated the phenomena, we think that this can do better and better. So here's some closing comments on this method, and then we can take some questions. So as we saw in the example Lucas presented, we have this kind of invariance along the middle of the field. So that is to say, if the ball was on the top versus on the bottom, it didn't matter. We would match those two together because the features were relative; they weren't absolute. And so the current method we have here is absolute because it's matching pixel to pixel. And so for some cases, we'll likely need to adapt and extend this method. There's one thing to note is that in some cases there may be many more untreated than treated cases, and if that's the case, then it might be possible to approximate the treated case exactly. So that is to make that IMED distance 0 using a convex combination of the untreated cases. When this is true, then then we might be able to solve a different optimization problem. That is to say, we might have multiple weights that would give us this perfect approximation result. If that's true, then we instead can think about maximizing the entropy of the weights subject to the perfect approximation constraint, i.e. the distance between the treated and the convex combination is equal to 0. So just to note the type of smoothing that one might use, this is an area of current investigation, and I think is actually quite an exciting area of research. So, I mentioned kernel regression here, you could do nearest neighbor smoothing. It's also possible to borrow from the work by Fernandez and our own Luke Bourne's work from their paper on wide open spaces, the field ownership model. So I'll just show a slide. So this is using our data. These are some examples of surfaces we created using their methodology, which incorporates movement vectors and so is temporal as well as spatial. So if you can construct surfaces that contain lots of information, you're likely to do better and better and better with this method. Again, in the interest of time, I'll end it there. I just want to thank everyone for showing up today and paying attention. This was a lot of fun, and again, thank you to my collaborators. And we're happy to take any questions.
Great, thanks very much, Aaron and Lucas. So yes, we are fairly short on time, but we can take questions by voice now. So actually, maybe I will actually scratch that. I'll get it to you to do on the Zoom chat so that I can ask them one at a time. I think it's probably the better idea. Those who obviously want to take off, maybe now would be a good time. Otherwise, we will stick around till at least 11:30. I will stick around. I'll keep the meeting open till at least 11:30 for those who want to ask more detailed questions after the initial round here. So we have one question right now from Alon. Um, so the underlying assumption of the DAGs, the graphs, and this research in general is that a shot is a reasonable metric for the outcome of an offensive play. Obviously, though, not all shots are created equally, and there are some metrics such as expected goals to differentiate one shot from another. Have you considered weighting the analysis based on the expected goals or similar metric of each shot in the outcome?
Yeah, yes, we have, and I don't know, Lucas. I don't know if you may want to speak to this one, the expected goal model. So we chose not to use goals as the outcome variable here because goals are very rare, and shot attempts are far more common. And so there's a question of defining a causal effect. And then, when you're out in the trenches, what's actually, the right thing to do. Presumably, if one is working for a team and has a lot more data than what we had, you have far more goals, observed goals in your data set, and you'd be able to say more. So we felt it was a little risky to do a causal analysis with such a rare. I don't know if Lucas, if you have any comments with the expected goal question.
Right. Yeah. If we have more data, and as you mentioned, like if we have more goals, right? So we can probably do that. But we only have 30 games, and then we have like I think roughly 20 or 30 goals compared. So that would be a very highly unbalanced data set to use that as the outcome, the response.
So hey guys, thanks for your answers. I just wanted to maybe clarify my question. So expected goals is a metric that you can, I'm not asking to weigh this only on goals, like replace T with, Y with goals. I understand why you chose shots for Y, because there's just not enough goals like you say. But I think there's already a metric out there, like a publicly available metric called expected goals to give a score to every one of these shots Y, right? To give them a value, and then weighting the whole analysis or parts of the analysis by not simply whether there was a shot Y 0 or 1, but a continuous variable of what the expected goals of Y was.
Right.
That's what I was trying to ask.
Right. Yeah. Okay. I see what I mean. So we actually build an expected goal model. So we actually assign, like a value attached to each shot. So like, to kind of quantify the quality of shots. But I think our challenge is, for the possession where it's not does not lead to a shot, like, and what would be the like expected goal for that, for that case?
I think they do assign a value even to non-shots, but that's a different question whether to incorporate that or not. But.
Yeah, and the other thing is that if you you were to use an expected goal model, you probably want to use separate data in order to estimate that expected goal model first. So you'd want to set some aside, because with if you think about it, if you want to respect the integrity of the DAG, the expected goal model is already doing something, right? There's already an implicit model there, and so you want to make sure you're not double using your data when you're doing that. So one approach might be to divide your data into different sets, create an expected goal model with one part of it, and then do a causal analysis with the part that you did not use to estimate the expected goal model.
Thanks.
So just for those of you, there will be a link. I'm just looking at the chat form currently. I will stop the recording and or provide the recording at a link to be determined later for those of you who are curious about that. I'm just going to, sorry, I'm just having some issues with my chat form here. Pop out. Okay, there we go. Okay, so there's a question from Dr. LeBlanc. Always include the, but this is a suggestion, always include the flipped configuration in your data to guarantee symmetry in your estimated probabilities. This is a simple trick when estimating symmetric functions non-parametrically, but might be computationally intensive.
Okay, cool. Yeah, thank you.
Okay, so Dr. LeBlanc, if you have anything to add to that, please jump in now. Otherwise, I'll go to the next question for Danny Chu.
Nope, not really. I'm good.
All right. Danny.
Yeah, Lucas, I just have a question about the graph in the end of your presentation. Could you just pull it up, please?
Sure, yeah.
Well, yeah, and I can ask the question while you're pulling it up. Is the effect that you quoted there the average effect across all of those propensity scores, or and is there a bigger difference at, like you mentioned, like the 0.6 to 1 range where we can see more of a difference? Is there a bigger treatment effect on those crosses? And so like those we're suggesting that people who didn't cross on when there's a high likelihood that they should have crossed it there.
Yeah, I think that's a great question. So yeah, so the quantity we estimated before, the average treatment effect is the average, is the mean, right? But this part is going to look at this average treatment effect like as the short probability as a function of the the probability of crossing. So yeah, exactly like you say. So if the probability of cross is kind of low, so probably and then the effect is smaller, and then if the probability of crossing is higher, like around 0.6, 0.7, that means you have a higher effect. Yeah.
Right. Okay. Cool. And I've heard a little bit, and this might be a bad question, but I've heard a little bit of like average treatment effect on the treated or on the control. So is this saying like if we get crossed on the non-cross attempts, we'd see 0.05 higher shot probability on average? Or is this just saying like in general over all crosses, or is this average treatment effect on all the plays or just on the ones that were not actually crossed?
This is actually on the average treatment effect on the treated, because yeah, we match all the the control with the treated group.
Right.
Yeah.
Right. So is that the same as would be like the average treatment effect on the control, like the counterfactual, if we had crossed on those cross attempts? No.
No, not really. So yeah, so if I go back to this part earlier, so here, so for the average treatment effect on treated, so we'll match all this control group with the observation in the treated, right? And then if we're doing average treatment effect on the control, so we're doing it like the other way. So we'll match all this treatment with the control.
Right. Okay.
Yeah, that would be a different quantity.
Gotcha. Okay. Cool. So this is answering the question then, like, are the crosses that they made the right choice? And then the other question that you could ask is like, should they have crossed on the other crosses?
Yeah, exactly. Yeah.
Awesome work, guys. This is like really, really cool.
Thanks.
Thank you.
Okay, so next question, back to Alon.
So just following up on what Danny said, it got me thinking, and I'm wondering if you could take sort of what he suggested for analysis and ask the question, when to cross? Like, when would the treatment be the highest? Because at the end of the day, for coaches, for actual practitioners of football, that's what matters, right? Like to build the strategy around that.
Mm-hmm. Yeah, and as we work through the problem, we've actually we've done that. So you have this, you can kind of define the expected benefit from crossing, and so you can then figure out when that's positive, then you should cross. You can then also optimize the expected value of a cross based on the spatial information. And so that'll give you the best possible situation. Yeah, that's an excellent question. Yeah. So that's what I would say is that's some work we've done, and that will appear in, I think, the third of this series of papers. You'll see that.
All right. So we don't have any questions left on the chat. So I think now is a good time to shut her down. If there's anyone who wants to chat afterwards, perhaps Aaron and Lucas, you can stay on for a couple more minutes. I'm willing to stay on until about 11:30, and then I have to move on. So with that, I'll thank our speakers very much. I don't know if my reactions are working here, but or not. But anyway, yeah, applause to you guys. And we will be back in a couple of weeks. I will send out information. We'll have 2 talks in June, and we have planned talks for July and August. If you're interested in speaking, please let me know. I would like to get, obviously, the group, external to SFU, like to recruit speakers. So, yeah, I hope this was good, enjoyable for you, and take care. Thanks very much for your attendance.
Thanks, everyone.
Good job, guys. Good work, fellas. Good job, Dave.